I have the pleasure to invite Professor Luciana Kassab of the Faculdade FATEC in São Paulo. Luciana. Luciana holds a bachelor degree in physics from the Pontifícia Universidade Católica de São Paulo, and also a Master of Science and PhD in science from the University of São Paulo. She's a full professor of physics at the Faculdade de Tecnologia, and she's dedicated to this faculty since 1994, and also has been director of the institution for 12 years, from 2006 to 2017. And also she leads pioneering work in research work in photonic glasses and novel nanocomposites for technological applications, waveguides using silicium technology, femtosecond lasers irradiation for integrated photonics, random lasers, color tunability, and white light generator. Please, Luciana, let's welcome Professor Luciana Kassab to the stage. Okay.
Aqui? Cadê o meu pai? Aqui. Well, I'd like to thank you very much for this kind invitation. I also congratulate you all for the hard work that let this conference become possible. I think that this conference plays an important role in our society and to all those that work with optics and photonics. I also congratulate Professor Paulo for his nice speech and all those that presented speeches of high level. I feel very glad seeing the students with a lot of motivation because you are very important for the development of our country, of course. This is the title of my talk. I am from Faculdade de Tecnologia de São Paulo, who was created around 50 years ago in the 70s. I've been there, as Professor said, since 1992, so far 30 years. And at this time, we have around 300 professors and around 3,000 students. We had more in the past, but after COVID, things changed. Faculty of Technology of São Paulo is located at the city center, for those that do not know. And this is the overview of my talk. First of all, I'd like to talk about the motivation for the use of these materials. Then I will discuss briefly the techniques used for the preparations. I'll go very quickly, showing you some of the applications we obtained in the last years that were already reported. And then I will focus on the waveguides that were produced using germanium dioxide, tellurium dioxide, using different technologies, the silicon technology and the ultra-fast processing by femtosecond laser irradiation. These materials have some interesting characteristics. They have a broad transmission window from visible to near to the mid-infrared region around 5,000 nanometers, high chemical stability, low melting temperature with respect to silicates and borates, low phonon energy, which is important for the non-radiative losses, high linear and non-linear refractive index, which is also important for ultra-fast response to devices, and they have demonstrated to be adequate hosts for the incorporation of metallic nanoparticles, and also for the incorporation of rare earth ions and for the nucleation of metallic nanoparticles. In fact, around 20 years ago, we demonstrated in this paper from Applied Physics Letters, it was the first demonstrated to nucleate metallic nanoparticles, silver nanoparticles, in germanate glass, and at the time we could show the improvement of on the optical properties of praseodymium ions. Since then, we have investigated these plasmonic effects in different situations. And more recently, we also showed the possibility of create nanoclusters, silver nanoclusters, in the same host. For those that do not know, the nanoclusters precede the stage of the formation of the metallic nanoparticles. They do not exhibit the plasmonic effects. They are amorphous, and they emit light in the broad band of the visible spectrum. And they are capable of transferring energy to the rare earth ions and to improve their photoluminescence. Several applications were demonstrated with these materials and reported. I list some of them here, but optical thermometry, lasers, random lasers, ultra-fast response devices, memory devices, cover to improve solar cell performance, passive and active waveguides, wearable device, among others. And here I show the steps used for the preparation of the glasses, the well-known melt quenching techniques. For those that are used to glasses, a familiar technique, a very simple one, in which we have, first we have the mixture of the reagents, followed by the quenching in a preheated brass mode, and the final step is the annealing. The annealing is performed to reduce the internal stress, which is an important step because it lets the sample become less fragile, mainly during polishing. It's also used to produce the metallic nanoparticles by thermal reduction. Of course, the time required for that depends on the material, on the viscosity of the material, meaning on the mobility of the metallic ions to form the neutral atoms. And the thin films are produced by the sputtering technique. We use a very simple equipment that operates in vacuum with argon gases, sometimes with a small concentration of oxygen, depending on the composition. We have 2 electrodes, so it's possible to perform co-sputtering of the materials. And at the top, sample holders, they rotate during the process, and this improves better uniformity and this improves the quality of the thin films. And here are the steps that we use for the preparation of the targets. Most of the targets are prepared by us, not only those of the hosts, but also the smallest ones that are here. The pellets, they are normally made of rare earth oxides, and they are used to dope our thin films. Now I'll briefly show you some of the results that were reported recently. In this case, by adding silver nanoparticles to this germanate composition, doped with 3 different ions, thulium, onbium, and terbium, it was possible to generate the white light. And by changing the concentration of these rare earth ions, we observed 2 different things. Tuning of the light from white to the green region, and tuning of the light from white to green yellow region. And of course, these results are due to the adequate concentrations of the rare earth ions that emit in the blue, red, and green, the well-known RGB, plus the plasmonic effects of the silver nanoparticles that improve, that change the optical properties of the material. Well, regarding the results with the photovoltaic devices, normally what happens in the literature is that the authors present the spectroscopic properties of the glasses, and in the end they say, well, they are potential candidates to be used in the photovoltaic devices, but they do not effectively show the performance of the photovoltaic device. They do not put the material in the device. And we do something different, as I illustrate in these 2 figures. We use different solar cell, a commercial silicon solar cell, and also multi-junction solar cell that's formed by layers of semiconductors material. The solar cell has applications has aerospatial applications. We cover with our glasses, the solar cell, and we use an immersion oil at the interface between the glass and the solar cell to reduce the reflection losses and improve the optical match. Then we perform the electric characterization. We mainly use the europium ions due to the strong red light that is emitted at about 600 nanometers. And then in this table, I show you the more important results. As you can see, we use different crystalline nanoparticles, metallic and dielectrical ones, silver, gold, and titanium. I think that titanium cannot be seen here, sorry. And then we calculate the efficiency of all this in all the situations, and the best result was found here when we used gold nanoparticles with an efficiency enhancement of about 18%. And the efficiency is calculated using the electrical parameters, voltage and current at the maximum power, the area of the solar cell, and the irradiance. And efficiency investment is calculated by comparing the efficiency of the solar cell with the one of the uncovered one. In this case, not only the luminescence of the material is important, but also the transmittance, both work together. And these are proof of concept results that can be used in different situations with different hosts, different rare earth ions, and more recently, some laboratories started to use this methodology and to cite our results. Well, up to now, active and passive devices were constructed on rigid substrates, and there is a lack in the literature regarding flexible substrates, flexible thin films that are largely used in wearable devices. For example, those sensors that are used to track the rate of glucose in the blood are made of wearable devices. And here is a very recent result, what was made in collaboration from the researchers in Trento, Professor Maurizio Ferrari and Alessandro Chiacera, and we showed for the first time the possibility of producing neodymium-doped telluride flexible thin films by the sputtering technique. In this image obtained by scanning electron microscopy, it's possible to see the thickness of the thin film of about 500 nanometers. It was deposited on a neutral flexible glass substrate with 0.1 millimeter thickness. That's 3 important emissions on neodymium could be measured by this experimental setup. And here I think it's not moving. It's not working. Yes, it is. It's possible to see that the flexibility of the substrate was not compromised by the presence of the telluride thin films. Adhesion was very good with respect to the silicate flexible thin films. And the refractive index of about 2 could be measured in the visible and near-infrared regions, even using transverse electric and magnetic polarizations, which means absence of birefringence. That's very important for some optical devices. In this figure, I show you the strong green emission, that is strong green light that comes from erbium ion from the up conversion process. It's another experiment that's under progress by a PhD student, in which used a different composition based on germanium dioxide. Now moving to the waveguides. Our waveguides were produced using different technologies, the silicon technology, and an ultrafast process that is based on the femtosecond laser irradiation. In this case, the waveguides are prepared using thin films in clean room, using the conventional microelectronics procedures that are based in photolithography and etching. For the case of the femtosecond irradiation, we use glasses with 2 millimeter thickness, and the waveguides are inscribed direct in the glass. Glasses of about 2 millimeter thickness are used in this case. In the other case, the thin films are of about 500 nanometers. I'm going to show you results that were already reported. In this case, 2 results of passive waveguides, and in the other case, 1 passive waveguide and 1 undoped glass, or a passive waveguide. There are many architectures that we use to produce these waveguides. At the beginning, we used the rib architecture, but in this case, we have a disadvantage because we have to etch the core of the material of the core. It's not that easy to etch heavy metal oxide materials. Normally, they are inert to etching procedures. And then we used another alternative, which is the pedestal waveguide. In this case, the first step is the preparation of the pedestal that's shown here in yellow. It's a silicon dioxide pedestal prepared in clean room, and the last step is the deposition of the core of the material. So you can, in this case, use any material you want. You have more flexibility than in the other case. Just for those that do not know, the core is a place where the light is going to be guided. Now, I will just show you the evolution of the process over the years very briefly. At the beginning, we used the chromium mask to prepare our patterns, but we have some problem. Sometimes the chromium is not totally removed, and we have the well-known micromasking effect, which is this columnar growth that compromises the guiding because they play the role of scatters. But well, these are the steps used in clean room. I'll not go into detail, but normally we take 1 week to finish. We have a protocol for that, but sometimes we change some of the steps in order to obtain waveguides with better performance. Then we change it. Instead of using this chromium mask, we started to use the silicon dioxide mask, and we obtained two interesting things: the reduction of the propagation losses, and as you can see in this image obtained by scanning electron microscopy, the absence of those sidewall ruggedness. More recently, we started to choose a different technology. It's a microwriter in which we are able to perform the direct write optical photolithography. In this case, we can draw any pattern we want. We have more flexibility. And the pattern is transferred to the photoresist by a laser that operates at about 385 nanometers. By using this new technology, we prepared neodymium-doped telluride thin films decorated with gold nanoparticles with the intention to see the plasmonic effects on the optical performance of the waveguide. Here I show you the setup used in our chamber. In one of the electrodes, we place the target of the host, a pellet of neodymium on it, and on the other target, on the other electrode, the target of gold. It's a commercial one with high purity. The last step in this case is not the core, but is the deposition of the gold also by sputtering. In this figure, I show you the final profile of our waveguide with 500 nanometers for the core, 600 nanometers for the pedestal high made of silicon dioxide. In this figure, I show you a waveguide with 4 micrometers diameter, but we produce different widths, as I'm going to show you. The relative gain is measured using this setup in which pump is performed at about 800 nanometer. The signal operates at 1 micrometer. It's sent to the sample and coupled to it by a lensed fiber with 2 micrometers diameter. And then at output side is sent to a spectrometer by an infrared fiber. The signal is collected to be then analyzed. And then we have here the results obtained. In fact, we have relative gain for different pump powers, for waveguides prepared with different widths, 4 micrometers, 8, 16, and 40 micrometers. The black curves are those related to the results of the waveguides that were prepared to be used as reference, in this case without gold nanoparticles, and the red ones related to the waveguides decorated with gold nanoparticles, and we can observe an enhancement in all cases that reaches up to 8% for the waveguide with 8 micrometers diameter. All these results are correlated to the photoluminescence enhancement that is attributed to the enhanced local field around these gold nanoparticles that increase the density of the neodymium ions that are excited, the well-known plasmonic effect. We performed the transmission electron microscopy measurements to evaluate these gold nanoparticles. In the figure, I show you the size distribution. We have many particles with diameters around 6 and 7 nanometers. This is an image in which I show you an isolated spherical particle. This is not clear, but this interplanar distance corresponds to the crystalline planes of gold, so corroborating the presence of gold nanoparticles in crystalline form. We repeated this experiment using different concentrations of neodymium. So instead of using just 1 pellet, we used 2 and 3 pellets of neodymium oxide and repeated the experiment. In this figure, I summarize all the results. In red, we have the results that correspond to the use of 2 pellets. In blue, 3 pellets. Black and gray, the results I showed you related to 1 pellet. In all the cases, we observe the enhancement due to the gold nanoparticles, but the best result refers to the lowest concentration of neodymium, the one in which we used just 1 pellet. Of course, this can be extended to different row hosts with different rare earth ions, with different applications for optical amplifiers with high performance. Now, using the same steps in clean room, the same experimental setup, and the same pedestal architecture, we only changed the configuration, as you can do it now by that microwriter, and we used the S-band configuration and performed the same measurements to determine the relative gain in these 2 situations, with and without gold nanoparticles. As in the other case, we observe an enhancement of more than 8%, again attributed to the plasmonic effects of the gold nanoparticles. Here I show the final profile of the waveguide with similar dimensions with respect to the other example I showed you, and the radius of our S-band with about 1 millimeters. And this is the first demonstration of the possibility of integrating the pedestal architecture with the S-band configuration with applications on compact on-chip optical amplifiers. And now I will move to the results obtained with the femtosecond laser irradiation. All these experiments were performed in collaboration with Centro de Lasers e Aplicações, do IPEM, located at IPEM, São Paulo. And this is, here I show you the setup we used. The sample is placed in this 3D translation stage that is perpendicular to this laser. It's a titanium sapphire laser that operates at about 800 nanometers, delivering pulses of 30 femtoseconds. In this case, we used a composition based on germanium dioxide because we based it on previous results in which interesting results about optical amplification at the third communication windows were obtained at about 1.5 micrometers, in this case in doping the material with ytterbium and erbium ions. But these results refers to the use of neodymium. And we had a problem here because neodymium absorptions at about 800 nanometers, which is in resonance with the operation of the laser we use for the femtosecond irradiation. So the sample heated, it fractured, and we had to look for a solution. We increased the velocity with respect to the other experiment, but in this case, we reduced the damage because the number of pulses was reduced, and we had another problem. The contrast between the refractive index was not enough to provide an ideal confinement of the light. And we overcame this problem by using several overlapped lines. In fact, our waveguides are formed by pair of parallel lines separated by 10 micrometers where light is guided. And now each of these lines are formed by several overlapped lines, and we choose different numbers 4 and 8, and they were determined empirically. Again, we determine the relative again by using a similar setup. The only difference is at the entrance. Now the light of the signal is coupled to the glass in a different way without using that lensed fiber but an objective lens. And here I show you results for the relative again, for samples with and without silver nanoparticles. Of course, we had to prepare those without silver nanoparticles to be used as reference. And hence, again, an enhancement of about 50% correlated to the photoluminescence increase, attributed again to the plasmonic effects of the silver nanoparticles. And here, we used an undoped glass, again, the same composition, but with different configurations, the S and the Y configuration. Here I show you the setup used, the configurations that were prepared, and the respective applications. For the Y configuration, it can be used as optical power dividers, power combiners, multiplexers, and the X band is mainly used to connect optical components. And here are the parameters used for the laser writing. They are based on previous studies that were reported here. Radius of 14 and 80 millimeters were used for the S band, and for the Y configuration, a distance of about 300 micrometers between the arms. In this case, we observed that below 40 millimeters radius, we observed higher propagation losses, so we did not use in this case. And above 300 micrometers, we did not observe this homogeneity in terms of the light propagation between the two arms. For example, for 600 micrometers, instead of having 49 here, we had something around 46. And this ratio, in fact, gives us the information of the uniformity between these two arms. By using this experimental setup, we will determine the propagation losses for all the cases, and the best result was found for the Y configuration, followed by the S band with 80 millimeters. I would like to highlight that these are not good numbers to be used because they limit miniaturization, but they can be used in situations where space is not a problem. They can be used to reduce reduce propagation losses. For example, if we connect two straight waveguides by an S-band, we will have lower propagation losses. If we connect them perpendicularly, the propagation losses will be higher. I think that these findings, they motivate the use of oxide glasses because they are rarely addressed in the literature in waveguides produced by this methodology. And finally, I'd like to say that the femtosecond writing methodology has advantages with respect to the silicon technology because we do not need to use the clean room, we do not need to develop those complex processes that involve several steps. However, our choice depends on the facilities we have in our lab and also on the applications we are looking for. I would like to acknowledge the National Institute of Photonics, Escola Politécnica da USP for the use of the clean room to prepare the silicon dioxide pedestal, Centro de Lasers e Aplicações do IPEM for the collaboration with the femtosecond laser irradiation to prepare our waveguides, Universidade de Pernambuco for the experiments with the photovoltaic devices, Institute for Photonics and Nanotechnologies for the collaboration with the flexible thin films. And finally, I thank the National Laboratory of Nanotechnology for the transmission electron microscopy measurements. And I thank all my students because without them, we do nothing, and you for your attention. Thank you very much.
Thank you, Luciana, for the nice presentation, excellent results also. So the poster, the presentation is open for questions.
I knew Katunda would do a question. I'm just joking.
Okay, no, I would have, I can talk to you later, but anyway, I didn't understand well, what do you attribute the enhancement in the optical amplifier neodymium doped? What is the effect of the
In doped on the doped?
Neodymium doped, you have an optical amplifier, and you compare the effect of the silver nanoparticles, I think.
I used both gold in the waveguide and silver in the book.
Yeah, my question is if the neodymium lifetime changes when you put the silver the metallic nanoparticle nearby, and if the enhancement of the amplifier is due to the increasing the emission cross-section or increasing in the excited state population?
In this case, yes, you're right. We increase the excited, the population. You have an impact on the stimulated emission and also on the ASI.
But you don't see any difference in the spontaneous emission lifetime?
Yes, I did not present.
You do see it?
Yes, of course.
Okay, thank you.
In the case of the silver, what happens is that during the laser processing, what happens is that the sample heats, so it promotes more nanoparticles by thermal reduction during the laser processing. In the case of the book, not in the case of the optical amplifier.
Okay, so other questions? Public? Luciana, so I have one question. How do you measure the refractive index difference between the core and the cladding of your waveguides? Have you ever measured the refractive index difference?
Yes, we measure it. I did not show.
Okay.
Because it's important to see the change. When you use the laser processing, you have nonlinear interactions with the material heats, and it changes not only optical properties but also the structure.
Okay, but can't you measure that later?
No, I measured it and I see the
You
change.
see the change.
It's at about 10-3. And when we put silver nanoparticles, this can go up to 10-4. So the higher the contrast between them, the better the confinement of the light.
Yes, yes. And how about, have you ever thought of also designing and writing more complex devices like modulators, possibly?
Can do it in the future, good idea. We use it straight and then we went to the Y configuration, and this Y is going to help us in the future to write the Mach-Zehnder interferometer, which is important with many applications. In the future, we intended to put graphene oxide on the top of the waveguides in order to produce an hybrid amplifier.
Okay, great. Yeah, thank you. Yeah. So if you do not have other questions, let's thank Luciana again. Thank you.
Thank you.
Okay.